Hello, everyone, and welcome. On behalf of our JCAP team and Caltech, it's my pleasure to welcome you to the virtual 2020 Solar Fuels meeting into our first webinar. Today's webinar will focus on renewable hydrogen generation. You can find more information about our meeting on our website. I will drop the link to the website into the chat shortly. As a kind reminder, please use the Q&A Zoom feature to submit your questions. After a live discussion that will conclude at 10 a.m. Pacific time, our panelists will respond to additional questions directly in the Q&A Zoom feature for another 30 minutes. So please stay tuned for that. So without too much delay, I would like to introduce today's moderator, Professor Harry Atwater. Harry is a director of JCAP program and Howard Hughes Professor of Applied Physics and Material Sciences at Caltech. Dr. Atwater's research interests center around two research themes: photovoltaic solar energy and plasmonics and optical materials. I also would like to welcome Sophia Housener. She is an associate professor in Laboratory of Renewable Energy and Sciences and Engineering at EPFL. She is joining us from Switzerland. Sophia leads the team that is working on both science and technology for efficient, inexpensive, sustainable, and durable approaches for renewable energy conversion. Sophia is also JCAP alumni, and she worked at LBNL. Welcome, Sophia. Alexis Bell is another panelist. He is a Dow Professor of Sustainable Chemistry at UC Berkeley and a faculty senior scientist at LBNL. He's also a member of research team at JCAP. Alex and his research group combine theory and experimental methods to study reaction mechanisms to identify parameters that govern activity and selectivity of catalysts. Joining us today is also Joel Ager. He's an adjunct professor of material science and engineering and staff scientist in the material sciences division at LBNL. Joel is a member of our JCAP family, and his research interests include development of new materials such as semiconductors, photoelectrochemical and electrochemical catalysts for solar to fuel conversion. I would also like to welcome Shannon Better. He is a professor of chemistry at University of Oregon. Shannon, and also he's a director of Oregon Center for Electrochemistry. Shannon and his research team work on designing, synthesizing, and understanding materials for applications in energy conversion and storage. So with that, I would like to conclude our brief introductions and turn this meeting over to Harry. Thank you.
Okay, thank you, Xenia, and thank you all for joining here. We're delighted to begin this first webinar of the JCAP 2020 Solar Fuel Science Meeting and welcome our friends and scientific colleagues from all around the world. So I'd like to begin just by framing, broadly the objectives of this entire webinar series, and then also the challenges associated with renewable hydrogen generation. And I think it's fair to say that for most of the people on this webinar, we all aspire to living in a world that looks something like the one on the left, where we have effectively an energy transformation, a transformation of our energy infrastructure from the current infrastructure that relies mainly on fossil fuel combustion for generation of energy, power, fuel for transportation, to one where we use renewable sources of energy, ultimately and fundamentally the sun, but also intermediate storage and other forms of energy such as wind and hydroelectric power generation to generate electricity or directly use sunlight to foster chemical transformations of water, and today we'll be talking about water splitting, carbon dioxide, and in fact we'll be talking about carbon dioxide in a subsequent webinar panel, and then also more recently quite a bit of interest in generation of reduced products of nitrogen, such as ammonia used for worldwide for fertilizer. And then with these primary reduced chemical feedstocks, we can envision a landscape where we generate fuels, chemicals, and materials from these reduced products in a way that allows us to sustain essentially everything that we make and do in our modern society. So fuels chemicals, materials for transportation, for agriculture, for industry, and residential use. And I think it's also that has given impetus, that this quest for such a world has given impetus to an area of solar fuel science, and that's what we're here to discuss today. And that solar fuel science enterprise is one that we've been excited to be part of for more than a decade, that involves fundamentally synthesis of materials and molecules that are used to drive these transformations, photoelectrochemical and electrocatalytic transformations, to characterize them, to understand their mechanisms, their structure, the things for catalysts which give rise to selectivity and activity, for photoelectrodes and photocatalysts, the things that allow charge carrier generation, to go, to understand the processes for going from the moment of prompt generation to charge carrier migration to the reaction center where the charges produce these chemical transformations. Then to actually test in an electrochemical environment the materials that are generated, and then to compare the results with the conjectures and predictions of theory, and in a sort of cyclic fashion, an iterative fashion, to generate new clues and improved processes. And in fact, we'll be hearing in a subsequent webinar about accelerated discovery, which represents an approach to accelerate this discovery loop. And then, of course, in the events where success results, is we have the possibility of generating technologies, or in our case, the science advances that give impetus to future technologies. And so that's, I think, something that's very motivating for all of the scientists in this field. So I wanted to just mention that today's subject is hydrogen. Hydrogen is itself a fuel, of course. It's an energy carrier, and it's a very high energy density energy carrier and fuel. But it's also a key constituent in established industrial routes for other very important chemical transformations. For example, the Fischer-Tropsch process for reduction of carbon dioxide, that is at least scaled to the pilot level in a number of locations around the world. And also, for example, for generation of methane by a hydrogen-mediated methanation process. And then finally, as alluded to earlier, the ammonia generation by the Haber-Bosch process. So currently, most hydrogen worldwide is generated by steam reforming of methane. And this is a reaction that, of course, generates or emits carbon dioxide. So in a world, the sustainable and renewable world, we'd like to replace that with an alternative CO2 emissions-free generation approach. And I should mention that even though most of the hydrogen generated worldwide is from steam reforming, about 4% of it currently comes, for example, from electrolytic formation, from water splitting. So it's beyond the research stage, but it's still at a very small stage of full-scale development. But we have alternatives, and there are a number of alternatives among inorganic chemical routes. They include solar thermochemical, high-temperature generation using metal oxide catalysts, low temperature electrolysis using a classical and well-established alkaline electrolyzer route, or a polymer electrolyte membrane electrolyzer route, or a high temperature electrolysis, which combines the features of thermochemical generation, accelerating the kinetics, reducing thermodynamic potentials, but using fundamentally an electrochemical driving force. And then finally, photoelectrochemical water splitting, which combines the energy harvesting from the sun directly with the electrochemical reduction and oxidation reactions. And so those reactions down here at the bottom of the slide, for both photochemical and electrochemical reactions for water splitting, center around an anodic reaction for generating protons and oxygen, which has a thermodynamic potential of 1.23 volts. And the generated protons in a solar fuels generator process then give rise to formation of hydrogen by combining with the generated electrons generated in a electrochemical or photoelectrochemical process. And So I'll just mention one other aspect to sort of seed the discussion that we're about to have, and that is that quite a bit has been learned about the catalytic properties of catalysts for oxygen evolution and hydrogen evolution. And this plot, which is a very classic set of data from a paper published in 2015 from the Charles McCrory and collaborators at JCAP, really compactly represents a lot of features about the catalysis for hydrogen evolution and oxygen evolution. And the net result of this is basically to show the activity, or excuse me, the overpotential at 10 milliamps per square centimeter current density for dark electrochemical hydrogen evolution against the at t equals 0, it's immediately when the catalyst is tested versus its catalytic overpotential 2 hours later. And also this color code indicates the roughness factor for the catalyst. And what you can see from this data is that for both acidic and basic solutions, we have many options for low overpotential catalysts for hydrogen evolution. Now on the oxygen evolution side, the story is quite a bit different. For oxygen evolution in acid or oxygen evolution in base, I should mention this data is from 2015, and there are some new candidates that we could add to this chart. But the story broadly is the same, that there are big challenges that from the point of view of generating low overpotentials for oxygen evolution. So this is an example, one of a number of science challenges that face us. So what I'd like to do now is to turn to our panel. So invite our panel to now join. And we'll begin with a discussion of some of the questions that face this field. And so I'd like to start that discussion with a question to the panel, which is what each of you regards as being the biggest advance in this field of renewable hydrogen generation in the last decade. So I'll go ahead and start with Sophia Housener to kick off that question.
Thank you, Harry. So I have, to myself, I would say there are two advancements in the last about 10 years, which I think are important. And the first one is that there has been sort of a sustainable and repeated demonstration of relatively high efficiency devices. And this has been done with a variety of different materials and sort of combinations, different membranes, whatnot. So I would say this is one important, let's say, achievement over the 10 years. And then a second one, which is particularly close to my heart, is sort of a shift towards actually integrating and device demonstration. So taking very well performing materials, components, photoelectrodes, membranes, and whatnot, and actually putting them together and trying to understand what is the integrational benefit and what is actually the performance in an integrated system. And then beyond that, starting to think about how to scale such a device and really going towards technology development. So these are the two, I would say, big achievements over the last 10 years.
Okay, great. Yeah, so now I'll pass the microphone to Alex Bell to weigh in on the same subject of the biggest advances in the last decade.
So I think that one of the biggest advances has been in characterizing the materials, particularly for the water oxidation, the difficult reaction that you pointed out, and identifying not only that platinum and iridium oxide are the two candidate catalysts for acidic conditions, iron nickel oxyhydroxide for basic conditions. These things have been known for a long time, but in the last 10 years, through use of X-ray absorption spectroscopy, other advanced techniques, also through the application of theory, it's now becoming clearer how the structure relates to the performance. And in the case of the iron nickel oxyhydroxide, it's now been established firmly that the iron component, which sometimes comes in fortuitously, is really the key element in making this an active catalyst under alkaline conditions.
Okay, great. Yeah, so now I'll ask Joel to weigh in on the same question.
Yeah, Harry, thank you for asking. I think a very significant advancement in the last decade has been how to make an integrated system work based on the fundamental understanding of what you need to do. The slide you showed showing the activity of the OER catalyst is just one part of the picture. If you want to realize an integrated device, you actually have to shepherd electrons to a cathode and holes to an anode without having them recombine. And we learned quite a lot how to make materials, some of which perform both functions, let's say passivation, protection, and catalysis, or put together different materials that work together to have the same function. And we do this by an understanding of what they individually do, from the mechanism of the OER reaction that Alex referred to, and also things we know about surface passivation from photovoltaics. By putting those together, we've been able to make some very nice integrated devices.
Okay, yeah, Shannon Betcher, biggest advances in the last 10 years.
Yeah, so I guess I have three. One of them builds off what Alex mentioned. And I think, you know, one of the really remarkable things about these catalysts is broadly, they're dynamic. So, you know, one of the things that has become increasingly important in understanding is how surfaces change under time, how species dissolve and redeposit, how the active sites are the most dynamic sites in many cases. And this actually correlates, you know, this idea that when you have a very stable chemical environment around a reactive site, it may not be a good catalyst and you might need some dynamics in the local bonding. And so really understanding that is not only something that has really taken off in the last 10 years, really due to efforts around the globe, but it's something that I see as a key thing going forward in the next 10 years. Another thing that I'm really excited about, maybe a little bit more specialized, but I think really big, is the advances in the last decade in actually alkaline membranes. So the solar fuels and electrochemistry, electrolysis industries have for a long time now, 30 or 40 years, used Nafion type acidic membranes to move protons. But as you pointed out, Harry, in the introduction, there's not a lot of materials that are stable under those locally acidic conditions, leads to challenges with critical elements. And what the polymer scientists have developed in the last 10 years, there are now several companies you can go out and buy hydroxide conducting membranes that work quite well. And I think we're poised actually to enable the next generation of alkaline technologies, both in electrolyzers, solar fuels devices, and fuel cells. And then the third one, which I think has really, really been huge, is theory and computation.
Yeah. Yeah,
so, you know, Alex mentioned this, you know, you look at the advances that have been made and how to understand catalytic reactions, not only on static surfaces, but on dynamic surfaces, using explicit water. You know, this is a huge, you know, the move from sort of a continuum description of solvent to actually looking at what the protons are doing and how they transfer and how the local bonding around the active site modulates. I mean, this has been a huge advance and again is poised for tremendous advance in the next decade. You know, MDQM methods that sample large configurational space and things like this, I think have been really huge and again, are going to have a continued impact as we move forward.
Yeah, that's right. I'm glad you brought up the increasing role of theory. It's really, you know, computing power has grown exponentially, and now that's starting to really pay off in first principles, detailed studies of heterogeneous and molecular catalyst environments. So now I'd like to turn back to Sophia and ask, given all the work that's been done in water splitting in the last decade, what about the gaps? Maybe we could identify 2 or 3 scientific and technological gaps that remain to be addressed in whole solar hydrogen generation.
Yeah, so I think to address this question, I myself took sort of a step back and thought about what are actually the requirements for such a device technology that it can become a significant player in this, let's say, energy economy and beyond. And this actually shows how difficult the challenge also is, because there is sort of a holistic requirements. There are technological requirements like the efficiency, production rates, but also something about stability, robustness, lifetime. And then there are requirements beyond that about cost economics, about sustainability, and then even, is this a simple system and can it be scaled? And so all of this has to simultaneously sort of be considered if we want to make a successful technology. And now if I think about the corresponding scientific challenges and technological challenges, to me, I would start with one which is really related to the stability, long-term performance. I think we have had lots of success of showing high performing devices, but maybe not for such a long time. And I think by long time, I mean months, years, tens of years, in fact. And so there is science as well as technology to be, let's say, focused on. And one of them is sort of understanding the local environment and how it affects the kinetics. So the competition, let's say, between water oxidation and the corresponding degradation, corrosion reaction. So this is more a scientific challenge. And at the same time, maybe a technology can also help. So can I find a way to sort of operate the device in a way that, let's say, corrosion or degradation might be less significant, thinking about a vapor phase based device, maybe compared to using a concentrated electrolyte. So that would be one challenge. Another one which I have seen also becoming more important is thinking about more realistic operating conditions. So if we design something, we design it for maybe one sun, 1.5 AM irradiation, but in reality our system is sort of exposed to varying conditions as input, so the solar energy, as well as the output. So potentially we do not want to produce continuously, or maybe we do want to produce continuously, whatnot. And so this has to be answered. And so again, I think from a scientific as well as a technological side, one can address this. How can I create a robust system? How does my material perform outside of the design point? And in terms of also technological advances, can I somehow address this with smart controlling approaches, a certain design of my flow conditions, batch versus continuous flow or whatnot. And then sort of the last or a third point is again trying to a little bit push more towards actually bringing this to a technology into a market where we have to go beyond materials, even devices. We have to start to think about a system which will introduce auxiliary devices, which will also sort of consume. Can we afford actually this? By how much will it reduce overall efficiency of our solar fuel technologies? I think there again, one can then look from both sides in a way, from a scientific side, because even it sounds very technological, but again, the dynamics of a whole system can be quite important. Understanding the coupled mass, heat transfer, charge transfer can be important. And then also thinking about flexibilization of such a system. How can it maybe work in off sometimes, which we have all the components ready, but effectively not using them, which would be bad for the economics. So yeah, these are a few, I would say, challenges, maybe a bit more on the technology side, particularly the last one.
Yeah, so I think basically nature gives us sunlight in predictable but nonetheless inevitable diurnal cycles. And those diurnal cycles have lots of complexity embedded with them for building a system that can operate to accommodate the changes in the diurnal cycle. Plus, we also, as you mentioned, we have to make systems that last a long time, over tens of thousands of diurnal cycles. So that's a big challenge. So I'd like to turn also to Joel Ager to ask about the gaps in science and technology, broad advances, and then maybe also touch upon the holy grail or religious question about integrated versus non-integrated solar fuels generators. Yeah.
Yeah, thank you, Harry. First, let me talk about the technology gap. What are we competing against? Well, you mentioned it in your introductory talk. It's a steam reforming of methane. And the gap between doing water electrolysis and steam reforming of methane has not always been fixed at a large level. In fact, in early part of the 20th century, water electrolysis was competitive with other ways of generating hydrogen. In fact, very large water splitting plants were built in places that had low electricity costs, for example, Canada. And a water electrolysis plant, quite a large one, operated in Norway into the later part of the 20th century. So it's a technology that we have some familiarity with. You should also point out that the steam reforming of methane is actually quite a bad process environmentally. Not only does it emit CO2, it requires very high temperatures, nearly 1,000 degrees C. So it's doubly contributing to greenhouse gases. So the challenge we have is actually finding a way to make green hydrogen production competitive again with steam reforming of methane. And I want to mention something we'll need to do in order to achieve that. Sophia mentioned reliability from a performance point of view, but I want to emphasize what you referred to, Harry, is the diurnal cycle of the sun that we want to use to drive the process. The processes into which we'll be feeding the hydrogen, let's say it's the production of methane or the countless other things that hydrogen does in chemical processing. They will want that hydrogen 24 hours a day, and we have a fluctuating source of sunlight. So we'll need to figure out a way to make the plants work reliably with the intermittent nature of the sun. In addition, they must be safe. And by safe, I mean safe to the workers that work in them and to the environment around them. Shannon may touch on this a little bit later when he gets to the materials choices that are used in the catalysts and components. But the system must not endanger anyone who works in it or around it. In fact, it should be safer and also cheaper than the steam reforming of methane that we now use. And the scientific challenge is to find a way to essentially buffer the input, which is light from the sun, in such a way that we can have a constant or even controllable production of hydrogen for the next processes that we'll use it.
Okay, yeah, that's a very interesting question. And in fact, yeah, we'll come back to that maybe in a later portion here to talk about ways that we can generate safety and how they fundamentally impact the processes. So I'd like to turn to Alex Bell now and ask, from a scientific perspective, are there still big challenges in understanding the water splitting reaction? You know, we've been touching on technology and science almost interchangeably. That's an exciting feature of this field that both are in play. What about the fundamental challenges remaining?
So I think there are still many challenges in this exciting area. The biggest one is understanding the connection between the material you make, how you make it, and its performance at the point where you can have an atomistic and molecular level description. And so you can predict how something is going to perform, how a material will perform after you have made it. So in your third introductory slide and in earlier discussion, we've highlighted iridium oxide as being a very good catalyst, a very scarce metal, but a good catalyst for acidic conditions of water splitting. Likewise, iron nickel oxyhydroxide, an earth-abundant compound that is good under alkaline conditions. Now, both of these have been known for decades. The problem is that if you read the literature, you discover that different investigators prepare their materials in different ways and have different outcomes. And one of the outcomes that is judged is the overpotential at a given current density. So for the non-specialist, maybe we should define what the overpotential means. It's the extra voltage that you have to apply to the catalyst to get a certain current density above and beyond what thermodynamics requires. So it's a metric of catalytic performance, and you want this number to be as low as possible. In the area of water splitting, water oxidation, nobody regularly beats 200 millivolts. So this is kind of a threshold at 10 milliamps per square centimeter. So let's go back and ask, why haven't we beaten that threshold? Part of it, I think, is because we don't know at the atomistic level exactly how these two key materials that have been identified empirically perform. So in the area of the alkaline condition, which I think may be the ultimate winner in terms of the material of choice for industrial processes, in fact, it's already used, but can be improved. The question is, where are the iron atoms in the context of the matrix of nickel oxyhydroxide? We know from the X-ray absorption spectroscopy that you substitute iron for nickel. It's a 3+ content, cation, but we don't know exactly where the iron sits, how close they are, And why is it that as you add more iron, you have some synergistic effects? So here's an opportunity for high-resolution electron microscopy to be carried out in situ, because it's one of the few techniques that might tell us exactly where the atoms sit in the matrix. And as has been pointed out, the system is dynamic. How do they move once you impose the voltage and the current is running? Also, this kind of microscopy would teach us how the material begins to degrade with time, and what atoms near the surface and in the bulk move around, and how does everything take place. So it's one thing to have this empirical experimental knowledge. The next thing is to capture this in the language of theory. So as has been mentioned earlier, theory has made remarkable advances in the area of electrocatalysis, but it's not yet precise enough to enable us to get rate coefficients for the individual elementary processes that can be put into a microkinetic model, enable us to predict precisely what is going to happen when we apply a potential to a material that's been produced in a certain way. So the ultimate goal here in the future is to have the precision of knowledge that now enables us to know exactly where the atoms sit in the material. So we have a good model from which to start the theory. Let the theory roll. The theory is now accurate enough on both energies and entropies to give us good rate coefficients. And we can see how both the chemistry and the material evolve. So I think there's a big spectrum of exciting opportunities.
Oops, sorry, I was muted there. So that's a great sort of telling through a sort of a vignette, a single scientific sort of thought experiment, hopefully will become a real experiment, the kind of challenges that lie ahead. So I want to also now turn to Shannon and ask about abundant and inexpensive water splitting catalyst. Do we need to use earth abundant materials? Are there other materials? And by the way, is there anything new with respect to hydrogen generation and water, dissociation of water?
Well, it's an interesting question. So whether we really need to use earth abundant materials, and the answer is, of course, yes. But then the question is at what scale? So I think, if you look at the worldwide production of something like iridium, which is a primary component in a electrolyzer, working in locally acidic conditions with an Nafion acidic membrane, you see that you can't scale to terawatt scales. Now, maybe we can get more iridium, maybe we can mine asteroids. There's lots of potential solutions there. But, that's not going to constrain the industry for the next 10 years. So the industry is going to grow probably exponentially for the next decade. Our goal then as scientists, I think, is to foresee the problems that industry will face in 10 or 20 years. And so, yes, in that context, we do need to replace these catalysts. And I think there's a huge opportunity actually in thinking about how we design earth abundant catalysts. And then, as you alluded to, how we control the local environments where chemical and electrochemical reactions take place. So I mentioned earlier this idea of switching from locally acidic membranes to locally basic membranes or alkaline conditions. And of course, as other panelists have mentioned, this is actually where electrolysis started in concentrated base and 100 years ago in large-scale electrolyzers. So if we can do this, that opens the door to a lot of different materials. The other really exciting advance that we've been really interested in is these so-called bipolar membranes. And these are really interesting. So you can basically take water and you pull it apart in the middle of a polymer membrane, and you can put the protons on one side to do a reaction, for example, take CO2 and make a reduced fuel, or take those protons to recombine them to make hydrogen. And you can do that in acidic conditions or a pH that's optimal for that particular reaction if you're talking about CO2 reduction. And then you can take the hydroxides and make oxygen. And making oxygen in a hydroxide-rich media is by far the preferred choice because you can use these earth-abundant materials. So there's a lot of, I think, new strategies, both to use membranes and catalyst design. And there's a huge parameter space in catalyst design when you start opening up the entire periodic table. And the key challenges are exactly what Alex and Joel have been mentioning is, you know, how do you search this huge space? How do you understand chemically what's going on? How do you look at that in our operando? How do you design for durability and efficiency? How do you integrate theory? They're all huge opportunities in this space.
Yeah, okay, yeah, I think it's a great point to touch on, because as we move from very effective water oxidation catalysts like iridium oxide to large scale, that really is a 15-year problem. So maybe I'll come back to Sophia and start with the question, where will we be in 10, 15 years from now in this field?
Yeah. Yeah, so predictions are of course always difficult to make, but maybe to sort of connect with what Shannon just mentioned before, I think sort of the next step in the shorter term time frame is maybe using these more rare materials and components, and maybe less integrated approaches for solar fuels. That can be PV plus electrolysis with power electronics, which right now is possible, but probably only in very specific ecosystems or environment economically interesting. But once we sort of follow this learning curve, they might become more interesting for other applications or areas as well. And there's might be hopefully sort of a self-activating path. And at the same time, the larger, let's say, the scale we're moving to, we have to move towards more abundant materials, potentially more integrated approaches. I think they have a large potential, sort of a disruptive potential in terms of cost, in terms of thinking about the process, potentially also in terms of what can be produced if we now even think about beyond hydrogen generation. And so this is sort of the longer term, I would say, and maybe even somewhere at the end of this line would then be also these photocatalytic particle suspensions. Who knows, this would be maybe more crazy out of the box ideas, but certainly also a lot of interesting science to do there.
Okay, yeah, so then I'll also turn over to Joel to ask the same question. 15 years from now, where will we be? And will systems look more integrated? Will they look fundamentally different from their prototypes that we have in the lab now? Where will we be?
Okay, so yeah, I'd like to, you gave a choice 5, 10, or 15 years, and I'll choose 10, right in the middle, Harry. And I think we will see actual demonstration projects of the type that Sophia was referring to in certain areas where it makes sense to locally generate hydrogen and other energy carriers. I happen to know that Japan and South Korea have projects along these lines. Right. Islands are very nice places to implement such technology demonstration projects, because the alternative is bringing fossil fuels to that island to generate power. And I think it's in those I'll call them pilot plant demonstrations that will be able to test out the sort of technologies and science we've been talking about in this meeting at a reasonable scale. And we will be able to get solar to hydrogen generation on a technological learning curve. And that will be a very strong driver in reducing costs. Many on this call will know the technology arc of photovoltaic solar cells, initially used to power satellites and fantastically expensive. And now, as many know, in areas with high insolation, they are the cheapest way to generate power, cheaper than any fossil fuel. And I see a similar technology arc for the sort of technologies we're discussing in this webinar. And we start by niche applications of the type that I referred to. And the time to start is right now, as has been realized by the projects that I'm talking about. And in 10 years, we'll see the fruits of those demonstrations.
Yeah, okay, so Alex, 5, 10, 15 years, where will we be?
So I think that in the coming decade, let me go that far at least, what we'll see is advancements in tools and methods that allow for operando observation of the materials that are used for water splitting, And these will be principally high-resolution electron microscopy done with operando cells. These already exist, but they need further refinement so that we can maintain the atomic scale resolution of the best microscopes. Also, we'll learn how to deal with the little problem of bubbles, which form when you have significant currents and a lot of product formation, which scatter electrons. But leaving that aside, what we'll be able to do once we solve these problems is to tell exactly where each of the elements sits in a complex matrix and whether they stay put with time or they move around. We'll have a better insight as to what are the elements of stability, what elementary processes occur, why do some materials degrade if prepared in a certain way and degrade to a lesser extent if prepared in another way. I think also, as Shannon has pointed out, that we'll see an increasing use of bipolar membranes. These are very exciting materials which are only now starting to be understood, both in terms of their performance and the theory applied to them. And we'll be able to take advantage of this for water splitting, but also for other applications such as CO2 reduction.
Okay, yeah, great. I think, again, touching on some of the science, so we've really spanned from science and technology. Now I'm going to come back to Sophia again and ask, what are two things that motivate you to work in this field? How do you get out of bed in the morning and get up and charge into the lab and work?
Well, so I think it's an extremely interesting, complex, multidisciplinary field, and I think this makes it very exciting, and so allows for interesting interactions and interesting sort of investigation and projects. So that's certainly one aspect. And then the other one, I think, is also that there is potentially a societal impact, in fact, thinking about our need to transition towards a more sustainable, renewable energy economy, providing more affordable green energy also to other parts of the world. And I think the hope to contribute also to this sort of, to have some impact there, these are two of my motivations to keep me going.
Okay, great. Yeah. So Joel, two things that motivate you in this field of hydrogen generation and water splitting.
Yeah, Harry, I'll just mention just one overarching one, if you don't mind. As a researcher in the physical sciences, I can't think of a more important problem to work on, actually. Of course, it's exciting, but many other fields are exciting as well. But this one, like Sophia said, has the potential to make a very important, I mean, you say societal, but also environmental impact. I think as I said, I can't think of something more relevant and important to work on. And it's one that demands the best efforts of scientists that span most of the physical sciences: chemistry, physics, engineering, material science, my own field, etc. And so that's what motivates me to go to the lab and work on this problem.
Okay, Alex, let me turn the mic to you. What motivates you? Two things.
Well, the first thing, as Joel has mentioned, is that we have an issue we're tackling which is of global importance. And that is to find economic and practical ways of providing the fuels and chemicals for the future in an environmentally responsible manner. And we've already illustrated how water splitting can be used to produce hydrogen without the co-production of CO2, using sunlight as the ultimate energy source. So this is an extremely important problem. As we've already identified, it's multidimensional. There are many elements of physics that are involved, many elements of engineering that are involved. And I personally find this an absolutely fascinating and challenging problem, particularly because nobody has the exact answer yet. People can claim specialization and ability to understand parts of the problem, but integrating the whole, all of the bits and pieces, all the microenvironments into a gestalt is something that is really challenging and exciting. And I'll add one more thing that gets me out of bed every morning and drives me to the computer these days. And that is that I get to work with very bright, talented young people. And there's nothing better than that to keep your juices flowing.
Okay, Shannon Betcher, before we turn to the audience for questions, a last word. What gets you out of bed in the morning?
I'll say we're in a race. Right. So we're in a race against climate change, against global warming. And to me, it's basically a coin flip, whether we win the race or global civilization crashes at this point. So, we need to do everything we can. And this is part of what I'm doing to try to, work on this. I mean, energy underlies everything. It underlies the world poverty, hunger, education. If you want to end poverty in, landlocked countries in Africa, you need to have cheap transport. You need cheap energy. There's probably no other way to do it. So, this is really, really important. So I'm really excited about that. And I'm actually, one thing I would say that I think I'm most excited about, if you look at this in the next 10 years, I think there's an real opportunity if science and technology converge for us to actually obsolete natural gas. And I think that would be just like PV is starting to obsolete aspects of fossil fuels once we can store that in hydrogen. And I think there is an economic argument that we're going to be able to do that in 10 or 15 years. Once we have a cent per kilowatt electricity from PV, which is coming, and we have low capital cost electrolyzers, I see us basically out-competing natural gas on a cost per joule basis. And, this is really exciting. It's just, can we do it in 10 years? Or is it going to be 50 years? And what's the damage to the earth before we get there? So that's what motivates me, is to really push this technology forward. Okay, great. So now we're going to turn to some of the audience questions. So what we'll do is take them in order that we've received from Xenia Masha Kelly. And so from Akalinder Singh comes a question: what are your thoughts on the development of ternary and quaternary oxides for PEC applications? What are the major challenges? So let's, ternary and quaternary oxides. Let me start off with Joel Ager on that one.
Yeah. Thank you for asking. You're referring back to the slide that Harry showed, had a lot of metals on it. The winners were iridium dioxide in acid and nickel iron in base. But actually, there's quite a lot of development of ternary oxides that are very promising, particularly those with the perovskite structure. These would be the old school perovskites, not containing organics or halides. And there's some open questions actually in exactly how these work that are as yet unaddressed. So we don't actually know their potential. I'm personally involved in some of that research using some of the tools that all the panelists have mentioned, including in situ X-ray spectroscopy, to figure out what the exact configuration of the surface is. So I think there's quite a bit of promise in that space. The high throughput efforts that JCAP's been engaged in have explored that space quite extensively from a compositional point of view. But what we're learning is that the degree to which the material remains crystalline or becomes partially amorphous as it evolves through the oxygen evolution reaction is actually the most important thing, including what atoms are expressed on the surface. And that's something that challenges us now from both an observational point of view, but also in a theory point of view, trying to go from first principles, what is the composition of electronic structure, to how the catalyst is actually going to behave when you operate it, is a significant challenge. I also want to double down on something I would like to mention in terms of reliability. We would like to make catalysts that can be regenerated. That is the natural system, as many people on the call know, does that. It works very hard for about 10 minutes and then has to rebuild its oxygen evolving catalyst. Right now, we don't know how to do that from first principles. And that's something I would like to see, not only initial performance from the catalyst, but also the ability to keep them going after they partially deactivate. That'll address some of the cost issues and scarcity issues that Shannon referred to.
Okay, great. Yeah, so I'm going to turn to the next question now from Mode Khan, who is asking, the perennial and maybe religious question. If we have cheap electricity available, then we can make green hydrogen at a competitive price versus steam reforming methane, steam reforming of methane. So where would this leave the field of integrated photoelectrochemical devices and photocatalysis? In other words, is there an opportunity beyond the indirect PV plus electrolysis for a PEC future? And so maybe I'll start with Sophia on that one.
Yeah, so first of all, maybe I would differ with this description and say that I don't think yet PV plus electrolyzer plus power electronics. I think it's an important point to realize that we need power electronics for such a system to be interesting at all, is already competitive with steam reforming. I think this is a false statement, or in very special environments. So Joel mentioned something about islands and environments like this, maybe decentralized, let's say production of ammonia where they need to truck in the hydrogen. So in some cases like this might be true, and therefore we need to do something to push this forward. And so of course now we can work. PV has already reached a remarkable low level, so one would then conclude mostly on the electrolyzer. One would have to go on this learning curve to make this more interesting. But I would argue that the integrated approach gives us additional benefits, one of them being potentially higher efficiencies, because I can actually first of all, make use of the thermal energy potentially as well. This is something we have particularly worked on, and therefore I'm quite aware of it. But there are other ways also. If you minimize distances, you have a lot smaller electronic losses. And so I really believe there is an efficiency advantage for integrated devices. And this, of course, then also translates into cost. Additionally, and that's the last point, you can also naively argue, I have two components, PV plus electrolysis, maybe three, power electronics, and I combine this all into one component. So you can argue now that most probably your costs will also go down. And this is particularly important when you think about for PV, the encasing, all these things become the important cost contributions these days. And if we think along the same lines, then the encasing will be in the important part. And so if you have one encasing for the three components instead of three individuals, again, I think one can make a cost argument. So I think there is something definitely for the integrated approach. Not even talking about catalysis and catalytic route, which might be accessible in an integrated approach, which is not accessible otherwise. So I think there is really a lot to the integrated approach.
Okay, yeah, no, I think that's a great way to frame it, is to say that when you really start digging into the system level, it's not at all clear that PV plus electrolysis is going to be an inexpensive, even though the cost of everything is coming down. It's important for the scientists to also pay attention to the economists and the people that are able to build accurate cost models for things that are operating at larger scales. And maybe a related question is coming from Dharmesh Hansora, who asks, what about the perception and scope of combining, for example, photovoltaic grade materials and metal oxide materials for large area integrated photoelectrodes? So many of the lab scale demonstrations that have solar fuels generators have been at a small scale. Is there an option? Is there a pathway in the near term, the medium term, long term for building sort of panel size structures? Shannon, what would you think about something like that? Is that, or do we have an outlook for that possibility?
Yeah, I mean, I think it's technologically possible right now. I mean, you could put together with PV grade materials, with some of the science advances in protection of those PV grade materials, you can put together a panel size demonstration unit. You need to think about some of the things Sophia has been mentioning, and that's transport lengths of ions. So that's one of the big advances actually in the integrated device field over the last 10 years, is understanding how all the ion flows in a sort of 3D finite element type model. So, we can do that. Will it be cost effective? No, not even close. Because you've just added a whole bunch of expensive components. You've had to, machine silicon wafers into the right sizes. I mean, it's a very expensive process. So So the question is, what science gets us to that outcome by a different route? So I think, going back to the kind of this coupled question of why are we pursuing these photoelectrochemical routes? I think you have to believe that the photoelectrochemical route, the integrated system, whether or not you're using embedded photovoltaic elements that are protected or photochemical junctions, it gives you different design parameters. It allows you to use, for example, smaller crystalline materials, allows you to use lower cost synthetic methods, allows you to potentially minimize balance of systems. So those are the things I want to emphasize. I think we can do the technology demonstrations. I would just argue it's probably not worth it unless we know we're shooting for a technology that can really compete. Until we do the science first and we're confident we can actually launch a technology, scaling up to me is maybe not the right strategy.
Okay, yeah, so we can scale, but the science is really important because it's going to allow us to scale with the ultimate efficiency, selectivity, and durability. So now there's I'll transition to a more holistic question, and this is from Claudio Amaya Santos, who's asking, we live in a fossil fuel dependent world where transportation and industry are emitting greenhouse gases and having a big impact on the environment. We talked about this earlier. How do we actually generate a artificial photosynthesis technology? If we imagine this scaling at a 15 years or longer from now to a very large scale technology, how do we do it without having artificial photosynthesis generate its own negative impacts on the environment and society? Who would like to try to have a crack at that question? Maybe I'll turn to Alex here for a first thought about that.
Okay, so the question is, would an alternative technology based on solar energy have an environmental impact? I think the critical element of what you just said, or the questioner's question. So this is an excellent question because there are some things that we don't know about. For example, in making the materials that we would need for either a PV and electrochemical system or an integrated photoelectrochemical system, would we be inadvertently or advertently generating CO2 and other toxic byproducts that over the lifetime of the system that we're trying to build, the alternative system, contribute as much in the way of environmental impact as the current fossil energy system? And this is a good question. It's a legitimate question, and it can be addressed by doing what's called life cycle analysis. So for any alternative, whether you're going to look at a hydrogen-driven automobile versus a gasoline-driven automobile, you have to look at where do the components of the automobile come from, where does the fuel come from, and over the life cycle of the system, is the output of CO2 or whatever environmental impact material you want to consider greater or smaller than the alternative. And I don't think that this has been done yet in the sphere of making chemicals or carbon-based fuels or even hydrogen for the systems we're talking about.
Yeah, okay, so Sophia, what about the prospect for impacts that are less than those of fossil fuels when we really scale such a system? How can we give an outlook on that?
Yeah, I think so. The tools of analysis, like what Alex mentioned, like life cycle analysis is definitely important, where you also look at toxicity of materials and so forth. But I think one point I want to mention still, there is no free lunch. We will have to pay for every artificial technology. We sort of have to pay for it. We just have to make sure comparatively we're better off than others. And what we compare to is coal or oil or whatnot. If you have seen a big coal field, you have potentially seen significant damage, not only by CO2 emissions, but also actually taking the coal out of the ground. So I think we really have to be, and the same also for natural gas, which is more relevant for hydrogen generation. But I think we have to be a little bit aware of this as well, because if it's out of sight, it's not necessarily not there. And I think many of the life cycle analyses which have been done have already shown quite clearly that almost all renewable alternatives are better than anything fossil fuel driven. So I think this is sort of my pragmatic answer, but having early on life cycle assessments in, let's say, the one of the tools to assess what you actually do and propose will also make sure that we early on can address potentially effects which we haven't seen right away as being problematic.
Okay, yeah, so I think that's a great outlook and a great place to wrap our webinar for today. I'll just note, we're not the first people to weigh in on this subject. Back in 1931, Thomas Edison, in a conversation with Henry Ford and Harvey Firestone, of course, who were the barons that initiated the auto industry, remarked, we're like tenant farmers chopping down the fence around our house for fuel when we should be using nature's inexhaustible sources of energy, sun, wind, and tide. And he said, I'd put my money on the sun and solar energy. What a source of power. And I hope we don't have to wait until all the oil and coal run out before we tackle that. So I think we're on a great start here in hydrogen generation. There are deep science questions embedded in this quest, but it's very interdisciplinary, and I think we all get motivation from the broader technology and societal context as well. So I'll turn it back to Xenia Amasha Kelly now, and thank the audience for joining this live discussion.
Great, thank you, Harry, and thank everyone for joining today. So I encourage everyone to stay for, if you have time, for another 30 minutes. We have lots of interesting questions, and our panelists will stay on for another 30 minutes and answer them in a Q&A. So if you have a question, please enter it in a Q&A Zoom section. And so thank you so much. And if you have any other questions for us, please contact us, visit our website, and have a wonderful Wednesday. Thank you. Take care.